we're doing introduction to the standard model. Okay. So last time we finished the discussion about the special relativity. I gave you homework as you saw. There might be some error in one part in one of the questions. I want to check it again before I'm giving a full announcement about that. Might be some typo there. I'll let you know, of course. And we started to discuss the standard model. And we said that the standard model is incomplete. In many ways. More people or nothing? We said that the standard model is incomplete in many ways. We said that some features are there, but we don't like them because we don't like fine-tuning. So maybe some parts are not so nice. Or added ad hoc. Good. Then I started to describe what it is. So I said in the standard model we have three types of particles. So the fundamental particles are 12 fundamental fermions. Fundamental fermions. They all have spin 1/2.
What did you write? There are
Added. Ad hoc. These are known as the matter particles. Matter particles like that. Then we say there are the interactions. So there are interactions. They are mediated by other types of particles, which are known as the spin 1 bosons or gauge bosons. And for each of the interactions that we have, there are the mediated bosons. For the electromagnetic, this is the photon, noted by gamma. For the weak, these are the two W and Z bosons. And for the strong, these are called the gluons. Noted by G. And the last part is the Higgs particle. Which is a spin 0 boson. That is needed to give mass to all of this nice construction. I think that's as far as we went to, as we managed to go last time. Questions? No? All is clear? Okay, so let's see. So now let's start discussing one by one. So the fundamental fermion, let's start with the matter particles. So these are the fermions. So far there's nothing too much technical, so there's really, in that sense it's not that interesting. So the fundamental fermions. So one is fundamental fermions. As I said, there are 12, and 12 types of them, and these are known as flavors. 12 known as flavors, without the U. So they're split into two. There are 6 flavors of quarks and 6 flavors of, you happen to know this, for leptons. There's certainly some symmetry here, which nobody really knows or really understands. We know it's there, but we don't really understand why it's there. If there's some part of a bigger symmetry or unknown. Now, partly these 12 flavors appear in 3 generations. They appear in 3 generations. Generation is also known as family. Families. Each family contains 4 members. Right? So we have each generation contains, so 1 neutral lepton, that's a neutrino. Don't get confused with a neutron. There is a neutron and a neutrino. It's a neutrino. 1 charged lepton. And 2 quarks. 1. A minute ago. There was a 1 up-type quark. Up-type quark. 1 down-type quark. Good board. So if we make a table, let's make a table here. So generation 1, generation 2, and generation 3. So what would be the neutral lepton of generation 1? Neutrino, right? Neutrino electron. It's electron neutrino. It's written as neutrino with electron neutrino or neutrino E, and its mass is very small but non-zero. Neutrino E is smaller than electron volt. What is the charged lepton of generation 1? It's simply the electron, that's right. And the mass of the electron, 511 MeV.
Why is that neutral? It's not charged?
It's not charged.
Okay.
It's not charged, that means neutral.
And what's special about electrons, or what make them different from quarks?
Different. Not many things. One step at a time.
Okay.
One step at a time. Then what is the up-type quark?
Up quark.
Simply the up quark, that's right. So U, up. The mass is heavier. M up is 2.3 MeV. And the down-type quark is obviously the down, which is heavier. M down is 4.8 MeV. That's the first generation. What's the second generation? Mu1. right? So the charge will be the muon. So there is a neutrino muon. Neutrino muon. That's the neutron lepton. And again, it has a very small mass, but non-zero. Then the muon. Questions?
Why there is a free generation? What is the logic?
There is no why. That is Mother Nature.
No, I asked why do we split them to three generations?
We will see.
Okay.
We will see. Wait. Don't jump. This is 106 MeV. So much heavier than the first generation. Then we have what will be the up-type quark? Nope.
So it's the charm.
Charm. It's called the charm. It's called the charm. That's much heavier. MC is 1.28 giga electron volt. It's for a particle, right? And that down type quark, strange, right? That's called the strange S. And the mass is actually less. Strange is 95 MeV. And the third generation, the tau, right? So we have neutrino tau.
Fields?
Again, the mass of the neutrino tau is very small, but not zero. There is the tau particle. All have a negative charge, right? Same as the muon and the electron. And the mass tau is 1.777 GeV. Then up-type quark. Top, right? This is the top quark. That's quite heavy. M top is 173 GeV. And then we have the bottom. And the mass of the bottom is lighter. And bottom is 4.2 GeV. And what is the electric charge of each one here? So charge. What is the charge of generation of the neutral leptons? Zero, right? Q is equal to 0. What is the charge of the charged lepton? -1. What is the charge of the up-type quark? 2/3. And what is the charge of the -1/3? So, to the best of our knowledge, these are the constituent of matter as we understand it. So these particles, right, they are there. Yes.
Right. Are we supposed to know what is a quark and what is a lepton? Like,
You will know at the end of, if you don't know at the end of this course what is a quark and what is a lepton, then you're really wasting your time here. You will know that.
You said like 6 quarks and 6 types. Like,
Yeah.
what is the difference?
Wait. That's it.
Oh, okay.
Everything will become clear. I told you, first I introduced, then we start to discuss each one individually.
What is the difference between generations?
You'll see that also. There are conservation laws between generations. Yeah.
לפני שגילו, אמרת שגילו את כל הקוואקים כאילו לפני אז 70 שנה, אז לפני שגילו אותם כל השישה האלה, כל ה-12 האלה, נחזו, נבדק עם כלום?
Oh, okay. This was a historical question. Yes and no. The last one to be discovered, I think, was the top quark, and it was in 1996. But it was predicted. But then there were several, the theory took time to develop, and it evolved. For example, in the 1960s, there were only 3 quarks known: up, down, and the charge. The strange quark came in 1974.
To
Was
the theory or
discussed.
to the theory or?
The theory evolved. The theory evolved. You know, there was an Israeli guy, Yuval Ne'eman. He wrote an interesting theory in the 1960s, but then there were only 3 quarks known back then: the up, down, and the charge.
מה שאני מתכוון לשאול זה כאילו את הקיום של כל ה-12 אתה יכול להשיג מהתיאוריה לבד?
כן, היום כן. The standard model is a standard model. It predicts all the...
ואתה יכול להשיג עוד חלקיקים כאלה או שרק...
No, that's a problem. No. Right, guys, everything will be done due time. This comes out of some symmetries. There are some symmetry groups from which we said that these are coming. Now, why are these symmetries? We don't know. Maybe they are part of a bigger symmetry. But this comes to bigger theories. Supersymmetry theory you might have heard of. The problem is we did not see any additional particles. This is what we've seen and measured. Maybe if you take this course in 20 years' time, there will be more particles discovered. That currently does not seem to be the case. That's the state of knowledge as we know today. Okay? The last particle that was discovered was the Higgs in 2014. Well, so that was more than 10 years ago. Okay? Yeah, yes.
Didn't you say that every particle is a matching antiparticle?
Yes.
So
I did not say it yet.
to be-
I did not say it yet because you stopped me in question.
You said it in the previous lecture,
Yeah.
I think. And where are they?
They are addition. These are the particles that exist in nature. It's a little bit of a lie because most of these particles, well, not most of, but some of these particles are not stable. So you don't really see them because they decay very fast into stable particles. For example, the only stable quarks that we have is the up and the down. These are the only ones that are stable. So we're all made of quarks up and down. There are other quarks, but they don't last very long. They can be generated, but then they decay and disappear after a very short time. Such is life. Okay.
אנחנו בקורס הזה נחזה את כל
קורס מבוא, חבר'ה. פעם. אחד. It's okay. It's okay. I can guarantee you that you will understand some things. I can guarantee you will not know everything at the end of this course. You need to take another course. Okay? So more interesting. Okay. Now, so as we said, these particles obey certain dynamics. Now, the dynamics of these particles obey the whole equation, which is known as Dirac equation. Right? The dynamics of these particles, the dynamics of each of the fundamental fermions is determined by the Dirac equation. Which in many ways is it's a relativistic generalization of Schrödinger's equation. And we will learn that. Now, this equation is completely symmetric between particles and antiparticles. So it actually predicts that in addition to these 12 particles, there will be 12 antiparticles, which will have equal masses but opposite charges. Okay, so in addition, this non-writing pen. In addition to the 12 particles, fermions, there are 12 anti-fermions. It's exactly the same mass but opposite charge. With same mass and opposite charge. That's not working either. So, what were the anti-particles of the charged leptons? How do I denote them? What would be the anti-electron? With the positron, right? So I'm simply writing as E plus, mu1 plus, and tau plus. That's the anti. What would be the anti-particles of the neutral leptons? So the neutrinos. I write them with the same, but with a bar on top of them. So it will be a neutrino E bar, neutrino mu bar, and neutrino tau bar. So that's fine. A little bit. And the same for the anti-quarks. So for the anti-quarks, again I put a bar which denotes an anti-quark. Okay, so I have an anti-up, anti-down, anti-charm, anti-strange, anti-top, and anti-bottom. And just one comment, as you'll see in a few minutes, when we say charge, we often think of electric charge. But there are other charges, such as the weak charge and the strong charge. So all these antiparticles carry anti-charges, but all of the anti-charges. So an anti-electron carries electromagnetic charge +1, but also the weak charge would be the opposite of that of the electron. Right?
So why we don't see other types of charges in the macro scale?
Who says we don't see them? Just have to know where to look. Okay, so let's think about charges. So I said that the particles interact with each other. There are three types of fundamental interactions. Well, there are four. Gravity, but gravity is not part of the standard model. So we neglect gravity. So we can think of these particles as make a table saying which type of charge, which type of interaction they respect or they respond to. So I can erase that one. So the properties of the fundamental fermions are characterized or categorized by the type of interaction they experience, by the type of interaction they experience. So we have several types of, well, three types of interactions. So let's look at the fermions. So fermions, we're making a table. strong, electromagnetic, and weak. So neutrinos, neutrino E, neutrino mu, neutrino tau. Do they interact via the strong interactions? Huh?
No,
No, they do not.
No,
No, they don't. Do they interact electromagnetically?
no, they don't have a charge.
No, they don't have a charge. Do they interact via the weak interaction?
Yes.
Yes, they do. What about the charged leptons? E, mu, tau. The charged leptons. Do they interact via the strong interaction?
If they were in nuclei, no?
No, yes, they do not. Do they interact electromagnetically?
Yes.
Yes, they do. Do they interact via the weak interactions?
Probably.
No.
Yes, they do. What about the
Just-
quarks?
You're just
They are babies.
What?
you're testing our general knowledge.
Yes.
Okay.
Do they interact via the strong interaction?
Yes.
Yes. Do they interact via the electromagnetic interaction?
Yes.
Yes, they carry charge. Do they interact via the weak interaction?
No.
Yes.
The beta,
Yes.
beta
Beta decay.
No.
Does the standard model predict a particle that not interact with anything? I know it's
No.
how can
pointless,
how
but
can
No.
you detect it if you
No. If it does not interact with anything,
I
you
know
cannot
it's
detect.
Part of the
pointless.
dark
but-
matter.
Yeah. Okay.
No. Yeah.
Does the standard model consider a Cooper couple as a boson?
That's not part of the standard model. This will be a boson, but it's part of statistical physics course. Because when you take a couple which are coupled, a couple of fermions, we can treat them as a boson if they are coupled. But that's not part of what happens here. So we say that a fermion is subject to the electromagnetic force if it carries an electromagnetic charge, which is not zero. And then we also say that it is subject to the strong force if it carries a strong charge. Very similarly. Now a strong charge has another name which is called color. Right, so let's see. Strong charge color. Of course, it's got nothing to do with colors that we see normally. So it's called a color charge. Color or color charge. And to further complicate things, the color charge itself comes in 3 different types, which are known as blue, green, and red, or red, green, and blue, RGB, right? So the color charge, comes in 3 different types. Known as RGB, red, green, and blue. Or RGB. will not surprise you to realize that in nature we only see quarks composed together such that the total color is white. Namely, they come either in threes, R, G, and B, or in twos, one with a G and one with an anti-G, for example. Of course, R, G, and B together are white, as we all know from your optics course.
They're also like cyan, yellow, and
No, they're only two. It's fundamental. It was fundamental particles.
זה משהו שיוצא מהמשוואות או שאנחנו חושבים שזה מה שראינו?
It's a symmetry group. Why it is such, I don't know. This is something that comes out of nature. And of course, from here, you'll find out immediately that there should be exactly 8 gluons, but we'll discuss that later.
אסף, לא הבנתי, מה אמרת עם שהם באים בזוגות?
I said, in nature, we don't see single quarks.
אוקיי.
We see a combination of quarks, and the combination is always such that the overall color is white.
אוקיי.
So they come either in threes, of course one of them will be red, one will be green, one will be blue, or they can come in pairs, one will be red and one will be anti-red.
אוקיי.
And these are the options. Okay? We'll discuss, I told you there are plenty of things to discuss here. Now, so all of them from here. Hey guys, all of them carry a weak charge because all of the fermions interact via the weak force. Okay, so we can say that all of them, all fermions carry weak charge. So the quarks, we said, are the only type of particles that carry the strong charge, the equivalent of just called the color charge. Right? The leptons do not carry the neutrinos do not carry the color. That's why it's called quantum chromodynamics. That's QCD. It's a quantum chromodynamics. I already mentioned that they are never observed as free particles, but always confined to bound states. And the bound states of hadrons, the bound states of quarks are known as, I just said it, hadrons. So quarks are never observed, are only observed in bound states. So they never appear by themselves. They never walk alone. And these bound states are basically what we call particles. These are called hadrons. There's a lot of terminology here. Guys, that's not appropriate.
You want some?
No, thank you. And that's not really appropriate. Okay. So these are known as hadrons. For example, what do you get when you take 2 up quarks and 1 down quark? Right. We call this a proton. What do you take? What do you get when you get two down quarks? And did everybody see that? No. The only thing that you can see is that what is the total charge? Two up quarks and one down quark. 1 plus 1. Right. What will happen when we get two down quarks and one up quark? What? That's a neutron. That's right. What is the charge? 0, right? 2/3 minus 1/3 minus 1/3 is 0. So, in fact, as I mentioned already, these are the only stable particles that there are. So that's why we're all made of them.
How do we know that these things true? That there is
I said so.
more? Yes.
How do we know what?
That there is something is smaller than proton and neutron.
We'll discuss it.
Okay.
Yeah.
But I think the neutron is not it's stable only for a few minutes. I know the other one not for.
Well, they're stable inside the kernel of an atom. If you take a free, you're right that if you take a free neutron, it will decay. We'll get to that shortly. That's really a beta decay. It's a standard decay. So yeah, so these are the only bound states, the only hadrons, the only hadrons that exist in a stable matter. And the reason is quite obvious from this table, right? These are the lightest quarks, right? These are much heavier, as you can see. Also, they're in the ground state. I didn't mention that, but you know, like any other particles that you're familiar from quantum mechanics, they can be in a ground state, but also in a first excited state, second excited state, etc. So I start realizing how many particles are actually made of all these 12 particles. Big number. Okay. All the particles that do not carry the strong force, namely these guys, collectively these are known as leptons. And the only stable leptons would be the electron and the 3 neutrinos. Which are kind of it's kind of interestingly stable. Yeah.
Could you please repeat your last sentence?
What?
About only leptons which are stable?
Yeah, the only stable leptons that there are the electron and the neutrino. So a tau lepton and a muon, these are not stable, they decay. They're relatively long, relative to the other particles, they are relatively long-lived. Why?
Speed.
No, because they interact via the weak interactions mainly. It makes them live longer, yes.
אפשר הבהרה, מה זה אומר יציבים אם ניקח המון זמן. בוודאות נגיד, החלקיקים שאתה אומר יציבים לא יתהפכו.
כן. זמן אקו. Yeah.
למה מתפרקים?
אין השם תכף נגיע לזה. כל אחד מתפרק וצמוני ודברים אחרים. כן.
The neutron, I know they oscillate between the
neutrino oscillation.
Does it count as stable?
Yeah, that's why I said it's sort of quasi-stable. They can oscillate between themselves. I don't think that in a short semester we'll have time to really discuss that. And fully honestly, I think it requires a little bit knowledge beyond what you do in undergrad. It requires a higher level to discuss it properly. But this maybe we can do, but I don't think we'll have time. have to see how fast we go. We can generate an extra lecture about that, but people have time. Yeah. Yeah, bound state is a state that is composed of several particles. So not a single one. Electron, you can have an electron free, right? And you can have an electron bound inside an atom. When I say bound state, it means it's not alone there. Okay? It's having a date already. More questions? Good. Okay. Good. Okay. So next thing we go is the forces. I mean, we said these are the 12 leptons that are basic ingredients of matter, as we understand it. Neglecting the matter we don't understand, such as dark matter or things like that. This is what we understand. Forces. Fundamental forces. Okay. So now we required some conceptual change from what you're familiar with in classical mechanics or E&M. When you learn E&M, how did you describe the force between particles?
What is it, ENM?
Electromagnetism. Oh. Voilà.
I think it was an A.
How do you describe forces? What? Potential. The potential, right? Yeah, so it's not going to work. Why it's not going to work? We cannot assume that particles interact via some potential, right? That's what you do in electromagnetism, that's what you do in Newtonian physics, right? There is a mass here, there is a potential, and there is another mass coming there. It feels the potential, so it changes its velocity, direction.
Even in quantum mechanics, we have some.
Even in quantum mechanics, you have that, right? You have the potential, the particle inside the potential
And
well, and then. So it's not working. Why it's not working? Two reasons. Why it cannot work?
Who said there is a potential?
What?
Who said there is a potential?
No, I mean, that's the way we describe it. Maxwell said it, right? Never. Newton said it. There are various ways of.
Because the forces comes from the particle, from colliding of particle and that stuff.
No. Yeah.
Maybe potential is like a field and we have single points that carry forces.
Yeah, but where does that come from? On a more fundamental basis. So there are two things here. Right, so in classical, well, it's not just classical, right? In classical and quantum mechanics, right? Classical and quantum mechanics. You used to think of forces. You think of forces as derived from a potential. But that does not work. Why not? One,
ואני יכול לשמר, לא חסרים לשמרים.
כן, כל אחד שאתה מכיר הם משמרים. חוץ מחיכוך, אנחנו זורם. חלק מכוח השמור. So it violates relativity. You cannot have, you cannot put a particle here, and immediately you would feel the potential somewhere there. So information must move at speed which cannot be larger than the speed of light. Actually, it does move at the speed of light. Yeah.
In electromagnetism, we talked about חוקולון המתוקן של פיינמן. ואז
That slightly helps, but still not fully. Yes. Okay, I know what you're talking about. The retarded potentials, basically. That's a way of making it look good. But no, yeah. Yeah.
הפוטנציאל מטייל זה לא תיקון מספיק טוב?
לא, התיקון הוא טוב מבחינה מתמטית, אבל קונספטואלית הוא לא נכון. Look, what you learn about retarded potential is correct mathematically. Conceptually, it's not working, but it's good enough, you know, potential is good enough to describe systems, so you have to stick with that. So, violates relativity. That's one fundamental problem. And the second fundamental problem, even if you say, okay, I can use retarded potential and I can overcome this problem, there is another fundamental problem, which is what?
החלקיקים האלה הם בכלל יוצרים את הפוטנציאל בעצמם, אז לא יכול להיות פוטנציאל משל עצמם, לא?
לא יכול להיות להם, אין בעיה. Something else? Yeah?
Isn't it require infinite energy?
No, I think this you can overcome. This is something you can overcome. Because anyway, you look at different potentials. You can get rid of infinities. Yeah?
When we talk about the bosons, do we say that maybe we need a medium of bosons so the force will move through it? Or not?
Yeah.
זה יכול להשתנות בין מערכות יחוס.
If you do it properly, you can live with that. No, okay, the fundamental problem is different. You can, and we've seen that, you can generate new particles. Right? You have one particle, what you'd say that, one particle decays into other particles. Now, if you work in the framework of potentials, this can never happen. Right? Potential can never create new particles. I mean, it can change it can apply force on a particle, it can change its motion, but it cannot produce new particles. Right? And you know, radioactivity, we do see new particles being created. Right? One particle decays into others. When particles collide, new particles are generated. So, generation of new particles. In interactions. Such as creation and annihilation of a pair of electron and positron. Right? You have two photons coming and producing a pair. Something which we see all the time. Yeah.
But like in quantum mechanics, we saw a potential of like quantum accelerator, and we know that the potential changes the quantum numbers. And here we see that the differences between particles is just the quantum numbers.
No. This is something else. These are different particles. They are particles that were not there, and they were generated in an interaction. So you need a new, different concept to describe that. Quantum mechanics does not allow you to generate new particles. It allows you to describe how the wave function of a particle, given that you have a particle, you can tell, okay, how the wave function evolves, how it changes with time, or whatever. Right? It does not let you generate new particles that were not there initially. You start with two particles, you can do scattering, right? Fermi's golden rule, do you know that? Yeah. No? Maybe? and then you know how you can do scattering in quantum mechanics amplitude for scattering, etc. That's fine, but you cannot generate the different particles than what we started with. And we do know that there exists, so we need something fundamentally different. More questions? Yeah.
Why can't we still use potential for it? Can't we?
Why? What?
למה עדיין אי אפשר להשתמש בפוטנציאל?
Because potential will never allow you to create new particles.
אי אפשר להוסיף עוד מימדים לפוטנציאל?
No. Okay. Maybe you can build a new theory. Let's come up with the theory that there is there. So, the solution, as I said, is within the framework of quantum field theory. So quantum field theory, QFT, the solution it proposes, saying that the particles are not there by themselves in a basic sense. So any interaction between two particles, two fermions, has to be mediated by one of those vector bosons, by gauge bosons. So any interaction in QFT, any interaction between two fermions is mediated by spin 1. It's also called a vector boson. One of the vector bosons that there are that I showed. Photon, W, Z, or gluon. So the force between the particles within this framework is simply an exchange of a particle. Okay? So one particle, suddenly I'll show that in a second. Now, for example, right? Let's say we want to describe interaction between two electrons, right? So we draw, it's called the Feynman diagram. So there is an electron, it's coming here, an electron is coming here. And then this electron would emit a photon and continue to move on. Now, because when it emits a photon, the form momentum is conserved between the electron and the photon. And of course, after it emits the photon, its form momentum will be different than the incoming one. And then this electron will interact with this photon, absorb it, and move away to with a different momentum than it started with. Overall, we would say that the electrons repelled each other. So we look from the outside, we say, oh, there was some force between them, between these two electrons, that caused them to change their trajectories. Okay? This is the way we describe interactions in quantum field theory.
So everything just exchanging photons?
No.
So
no. This is electromagnetic. If it's a strong force, what would they exchange? If it was a strong force, gluons. They would exchange gluons.
Okay. How the electron knows to emit photon to the other electron everywhere?
That's an excellent question. It does emit a photon everywhere. And this photon is not a real photon. Right? This is a virtual photon. You can never measure the properties of this photon because this photon is below the ability to observe it given the Heisenberg's uncertainty principle. So, we say for example, in electromagnetic interaction between charged particles, there is an exchange of photon, but I am emphasizing this is a virtual photon of a virtual virtual photon. Basically, we think of it as a quantum fluctuations of space, which existence is limited by the uncertainty principle, whose existence is limited
What does that mean?
by the uncertainty principle. But it does carry some of the characteristics of real particle. Okay? Now, but as opposed to real particle, let's see, what does it mean? Existence is limited by the uncertainty principle. As opposed to the real particle, it does not obey the standard relation between E, M, and P. So, it does not obey the energy momentum relation, namely m squared is equal E squared minus P squared. Which means that its kinetic energy is ill-determined. Now, the technical term for that, you'll see, it's called off the mass shell. It is off the mass shell.
What does it mean?
You'll get to know that shortly. It's a theoretical description of how do we describe interactions between two particles. The advantage, it's a virtual photon. It's not a photon that can ever be measured. It cannot exist for long enough time. Okay? It can never exist for long enough time for any of us to be measured. Momentum and energy are conserved in each of the vertices that there are. Okay? So this photon is really there, in a sense, to describe the transformation of energy and momentum between the colliding particles. Wait, it's not there yet. Now, I'll say a few more words. I'll let you time for questions, but I want to finish with a few things because I know what I'm saying now is confusing, given that's the first time that you're seeing that, I assume. Now, I did not mention that. I mean, this is a Feynman diagram, obviously. Time goes from left to right, so this is time. Now, of course, so in this description, the upper electron emits a photon, it goes away, and then this photon is absorbed by the lower electron, which then goes away. Of course, everything works, so it can be exactly the opposite. So we can have a situation where the lower electron emits a photon, and then this photon is only later on absorbed by the upper electron. Now, since of course I said we cannot really see that, what we do see is only the combined effect of these two diagrams. Okay, now okay. Now before I'm going to answer questions, why can we do it? Why it is allowed to do all these things? Again, for that you need to study quantum field theory, which is only given after you postgraduate studies. Basically, the same way as in quantum mechanics, right? You're taking from classical mechanics to quantum mechanics. Quantum. You're promoting certain observables into operators. Right? E becomes an operator, P, momentum becomes an operator, right? Then when you go from quantum, and these operators, they operate on wave function, right? Psi, right? From quantum mechanics to quantum field theory, the field is promoted to an operator. In fact, an infinitely large, I mean, we will discuss that slightly in some hints, or some basically. The field itself becomes so the wave function itself is promoted into operators. There's some notations called second quantization. The field becomes an operator. Actually, it's a set of infinite number of operators. Now, operating on what?
Vacuum.
On the vacuum. So the space now is not just a Hilbert space in which you can describe a single particle. It's called a Fock space. Just out of curiosity, did you hear about Fock space? So, yes. Which course?
אני בתור שלי.
בתור שלי. So it's not Fock space. What? You learned quantum field theory?
I was in a summer school. Small courses. Small.
So the field is also quantum field theory, right? This is promoted to a field which operates on a vacuum. When it operates on a vacuum, it can excite it. The same way as harmonic oscillator, there is a rising operator and a lowering operator. With harmonic oscillator, exactly the same thing. So it can excite the vacuum. When it excites the vacuum, this we call particle. So in reality, what we have is a field for every particle. And all the fields can excite and de-excite the vacuum state. Okay?
And the Fock space is what in this?
Fock space is a space which enables you, it's a generalization of Hilbert space for multiple particle space. Okay?
So
very hand-wavingly without getting into anything. Yeah.
This is how we explain שהקרני שמש מגיעות אלינו, כאילו, דרך.
No. This explains interactions between particles.
כן, אבל...
The sun rays, the sun rays they go through vacuum. They don't interact with the vacuum.
They don't interact.
That's why they just can go not from the stars, from the sun. For every star, right? From stars, the other galaxies we see them. They go through the vacuum without interfering with the vacuum. This is the way we explain the things that we can see are initially 2 electrons and finally 2 electrons. This we cannot see. It's a virtual particle. It's a quantum fluctuations really. Yes.
In this diagram, we see the electron interact only one time, but in electromagnetism, we saw the interaction is like continuous. So.
Wait. You're right. One step at a time. Wait. Yeah, you want to go first.
Yeah. With this vacuum, we can characterize the spontaneous emission from atoms.
Yes, it's a decay, basically. Yeah. No, this is just it's a cartoon.
Huh?
It's a cartoon. The y-axis, you mean?
Yeah.
Cartoon. Okay. guys, I know it's getting more messy. It's okay, we'll get into one step at a time. I'm giving you the broad overview of what we're going to do here this semester.
So it's an overview. We will get more into details.
Some. I cannot get you into all of it.
Yeah, I'm
because
not
it's
talking about
next
the
to
final diagram.
you'll know enough. Okay? Fully deriving the Feynman diagrams, that's a course in quantum field theory. Here I will teach you how to use them. What they mean and how to use them. Guys, questions? You know, that was an important remark. I mean, in a course in quantum field theory, you learn exactly how you derive these Feynman diagrams. And you'll see that there is some nesty integrals. There's many delta functions involved. Everything miraculously ends up nicely. In this course, I think I will show you some, but we won't get the full derivative of everything, but I will show you how it works and you'll know how to use these things. Okay, so again, this is why it's called the first course. The second course, then it will be more one step at a time. Okay, so each of the three forces relevant to the particle physics is described by exchange of spin 1 particle with gauge boson. So we said we already described the gauge boson, so we said let's go over that briefly. So the gauge bosons. So one is the photon. We already saw that photon. It's massless and gamma equal to 0. Then we have the weak interaction. That's responsible for the beta decay. Beta decay is normally what you see in decay all the time. So beta decay is when a neutron is going to proton plus what? What? Electron. Charge is concerned plus anti-neutrino electron because electron number needs to be conserved as well. But you see nuclear fusion as well. This is mediated by the it's N. That's mediated by the W and Z bosons. So W plus minus mass is 80 GeV and Z is both charged 80, slightly heavier, 21 GeV. And the strong interaction, we said these are the gluons. The G's, there are 8 of them. That we'll see why. They are massless. So M gluons, there are 8 such. Again, it comes from a nice symmetry. 8 gluons, each carrying a different color charge.
So like 24?
What?
So like 24, like 8 times 4 colors? Or
8. The charge carrying are the quarks. But the gluon can connect one quark to another quark. We'll go through. The gluons carrying color charge. Okay. In general, as opposed to the photon, it does not carry any charge. Everything else do carry charges. Okay. I mean, the W plus minus obviously carry electromagnetic charge. Right? So they do carry charges, which means that the charge can exchange. I mean, here, right? Charge is exchanged, right? Neutron goes into protons plus electron plus antineutrino. Yeah.
גלונים
something has a zero mass, it will move at the speed of light. But as we'll see, they are very short. They exist only in a very short length scale, but they cannot go outside of the kernel. They're just connecting the quarks, which by themselves has to come in bound states. They don't come independently. We don't see free quarks around here. Yeah.
How can you show in an experiment that a particle is zero mass?
Again, you cannot show zero mass because you cannot show that something does not exist. What you can show is that it is consistent with zero. Okay? And it's theoretically consistent. Theoretically it's zero, and experimentally it is consistent with zero. This is the only thing you can show.
In the first lecture, I think, you said one of the problems of the standard model is that there are 19 variables. Are the masslessity of gluons and photons is part of it, or is it?
Yeah, the masses in general. I mean, if you want, we go over all the list, but generally the masses.
But is the point of is like one of the free values, כאילו אחד המשתנים החופשיים הוא העובדה שהפוטון חסר מסה?
I think so, yeah. I think that the masses of the photons is one.
גלואונים כל השמונה גם מספרים?
No, these are not free particles. They come out of symmetries. There is, it's obviously it's connected to the fact that there are three generations, three colors for each quark. Right? Everything is connected. We will discuss symmetries. We'll see. It's very nice. But one thing at a time. We cannot go over everything. Any further people from the back? More? No? Yes, maybe. Okay. So Feynman diagrams. So I just draw Feynman diagrams. Here comes something which I always get annoyed by. I'll just say to you, and you will forgive me. So, this is the essential part of the particle physics. Essentially, they represent a Feynman diagram represents a transition between different states. Everything is time ordering. Now, the natural or the basic ingredient of Feynman diagram is the vortex. Quote. Okay. Coupling of fermions and bosons are described in or by vertices. Vertices. I think both ways are legitimate. But codeine. So these are the basic constitutions of Feynman diagrams. So QED, electromagnetism. Well, this we already showed. Right? All charged particles. Now I should mention, I didn't mention that. I mean, I saw that there is time. Time goes from left to right. But I said that we actually have to sum over the ones in which the upper electron emits a photon and then the one in which the lower electron emits a photon first. So really, it doesn't really matter. We just sum all of them. Each diagram represents all of the possibilities of a single photon. So there is the vertex here. Now, this is how you represent the photon. E minus photon. Just to make sure we all speak in the same language, right? So as you saw, electrons, normally fermions I would have with a line, simple lines, with an arrow. Arrow represents a charge. So if it's a positron, it will be the opposite arrow. We'll see that in a second. Photon is a wiggly line, strong. That's between the quarks. So there is a quark, They exchange a gluon, and the gluon would be like a spring. And there is a weak, and the weak is a bit more tricky because you can have two. You can have one with charge, W, one without a charge, which is the Z. So for example, you can have an electron that transfers its charge to the W. Here comes another annoying thing, just a second, and ends up as a neutrino. Now, I'm used to write down the mediators of the weak by a dashed line. I think in some textbooks you'll find that, but in other textbooks you'll find that, of course, a W minus. In other textbooks you'll fill it in a similar way to the photon. Or you can have a neutrino with Z.
So how do you know when it's
It will be written, but yeah, I'm used to that notation. I don't even know when the
it looks better because you can
So if you read textbooks, which you should, in some textbooks you'll find this, in some textbooks you'll find this. I don't know who decided to switch and why and when. Yeah.
Can the electron emit W plus?
No.
Why not?
Then what? What will it turn into? In each vertex, there are several conserved quantities.
If it was a positron, then it
If it was a positron, it will W plus.
Or a neutrino.
Yeah, we'll go. That is important, so we'll go to that soon. Yeah.
Previously, when we saw two electrons interact with a photon, is it like one of them emits and the other collect, or like they both emit and collect, they both exchange photons?
What I showed
Yes.
was electron interacting with another electron.
Yes, but with
The
a
photon was a virtual photon,
Yes, but it's like one of them emitting it and the other collecting it, or
absorbing.
absorbing it, or
Yes.
is it they exchange both?
It's both. I said it's a sum of all the options. Slowly but surely we'll get there. It's the sum of all the options. So note that we always have vertices of 3 points. So it's very simple vertices. It's always 3-point vertices. Right? We never have vertices of 4, 5, and 6 points. Only 3-point vertices. So only one single particle is emitted or absorbed. Okay. Right. Now a particle can interact with a given boson, gauge boson, only if they carry the same charge. Right. So that's why, for example, electron or neutron can never couple to a gluon. Right? Because the electron does not carry the color charge, which the gluon does.
But the photon doesn't have any charge.
Electromagnetic charge. Sorry. I said that in QED, a photon is the mediator of electromagnetic interactions.
Oh. So because
So everything that
electron
interacts
doesn't,
electromagnetically would interact with a photon.
Oh.
Yeah.
Can you say, I know the photon has a spin of 1. Can you,
Yeah.
how can you like specify where it, how
can you see that the...
We will. Again, this is a virtual photon. We cannot see the photon by itself. Yeah.
You said that we will only have 3-point vertices.
Yeah.
Is it possible for emission of virtual emission of more than one?
It's not only possible, you have to take it into account. For example, in the interaction between two electrons, right, we draw that. But I could also draw that.
But not simultaneous.
No, it's not simultaneously, but you can have exchange. You not only can, you will have exchange. In fact, you have infinitely many, and you have to sum them all.
But simultaneously is not possible?
No, no, it's not
No,
simultaneous.
that's all.
You have to sum them all. Fortunately, well, you're jumping, so that's why I prefer that we wait with the questions, because then they never end anyway. To every vertex, there is a coupling. There's a coupling.
What you've done before.
No, guys, I'll finish now. I'll continue now, and then there'll be time for questions. Otherwise, we won't get anywhere. Right. So, we said a particle interacts with a force carrying. Saying right. Yes, boson. Only if they carries the charge of the interaction. So, within a Feynman diagram, the vertex, that's the location where particles are created and destroyed. Okay? Particles are created and destroyed at the vertex. At the vertex. The form momentum is conserved. So for example, when we speak about this diagram, let's say that this, hey guys, questions? If the initially coming electron has momentum p mu 1, and the outgoing electron would have momentum p mu 2, and the photon will have form momentum, let's say q mu. Since the form momentum is conserved at the vertex, that means that P1 mu is P2 mu plus Q mu. Always. Which makes it very easy to do calculations. Now, there are other conserved quantities. In fact, in each vertex there are many conserved quantities. Angular momentum is conserved, charge is conserved, leptonic and baryonic numbers, which I did not define what they are conserved. Strangeness is conserved, parity is conserved. There are many conserved quantities.
Strangeness?
Yeah.
That was
You have a lot of it.
Thank you.
Now I said the arrows represent flow of charge. Now here comes the key. For each type of interaction, there is an associated coupling constant. Okay? To each type of interaction, there is an associated coupling constant. Normally it's noted by G. What's in it represents the strengths of the interaction. Yes. It represents basically, you can think of it, it's you know, what is the probability of this fermion to emit or absorb a photon, for example. Okay, essentially this will tell us how strong the force is going to be. Now, this is essentially what enables us to make useful calculations. I'm not exactly running, right? Because I said, if you want to describe interactions between particles, let's say scattering of electrons, right? Then the first order Feynman diagram would look like that. But we also have Feynman diagrams that would look like that. Right? So here there is an exchange of one photon between the particles. Here there is an exchange of two photons. Go on. Exchange of 3 photons, 4 photons, million photons. It's virtual, infinitely. But here comes the trick, right? There is a coupling here. Coupling here is G. You might know what is this coupling constant for electromagnetism. This is the fine structure constant, which you might have heard of, right? So here you have 2 such couplings. So you have G squared. Here you have 4. So you have G to the 4. Now if G is small, if G is very small, much smaller than unity, right? For example, in electromagnetism, it's the fine structure constant. Does anybody happen to know what it is? Right, 1 over 100. So approximately 1%. Right? So that means that the contribution. Now this coupling constant is what enters what's called the matrix element, which essentially will tell us what is the probability for that to happen. That enables us to make actual calculations. What will be the force between them, what will be the rate of decay. Right, that's what actually something which we actually measure. This is very small, much more than 1. Then fortunately for us, we can simply ignore all the higher order corrections because they are very small. The problem is what happens when this is not so small than 1. Yes?
Aren't there an infinite number of like much smaller than 1? So isn't it adding to more than much smaller than?
Yes. This again goes into how to sum up infinities. That's quantum field theory 2. Okay, there are ways of doing that. Very nice ways how to solve infinities. Sometimes you can do that. Sometimes you cannot do that. Okay, that's part of the reason why we think that. Why I told you that the standard model is incomplete. Now, for weak interaction, it's very simple, right? This is 1 over 137, so it's small. Electromagnetic, sorry. Weak interaction is slightly higher, actually.
1 over 30.
1 over 30, right. For the strong, 1. About 1.
Much stronger.
Yes, strong. It's about 1. Which means that doing these calculations for the strong is a nightmare. But people have done that. Or find some ways of doing some things which make sense and can be tested. Yes.
הג'אז הוא גם בג'יגה אלקטרון וולט?
What?
כאילו קבוע ההצמדה הזאת.
It's a unit less. It does not have any units.
לכל הבוזונים?
Yeah, it doesn't have any units. Not for the bosons, for the interactions.
Okay.
For the interactions. Yes.
So, with higher G, it's more probable for this interaction to happen? It's more
Not necessarily, no. It's a bit more complicated than that. Electromagnetic interactions are more common than weak interactions, and the reason is that in weak interactions you're producing W and Z bosons, which are very massive. There are a lot of energy in them, right? They are very massive. Photon is massless, so it's much easier to produce a photon.
So it just says the weight of the...
Yeah, so you can think of it as the probability of interaction. So this is the probability of this electron to interact with a photon, is G. Okay? Or probability of a spin half essentially it is the strength of the interaction. This will be mathematical representation, numerical representation of the strength of an interaction. Okay? So again, just the probability of this electron to either emit or absorb a photon, which is of course completely symmetric. Okay? More questions? Okay, can I take a few more minutes? Yeah, anyway, we'll be happy to. So, these are the fundamental ingredients, right? But so how do we represent physical processes? Right? That's what we're interested in. Essentially, there are two types of processes we're really interested in. Right? One is interaction between particles, right? Like here. We have interaction between two electrons. The other one is the decay of one particle into other particles. Erase it already. Right. What? Electron will not decay to neutron. I said. No, it cannot decay to a neutrino by itself. I said that there are, but beta decay, a neutron can decay into a proton and an electron and anti-electron. Right? In fact, what really decays there is a down quark. One down quark turns into an up quark, which is allowed because the down quark is slightly more heavy than the up quark. Okay? So, description of physical interactions, physical processes. Sorry. Description of physical processes. So essentially, a Feynman diagram is just a collection of vertices. So the basic ingredient is a vertex, and the Feynman diagram is a simple collection of vertices. Right, so I basically already told you that if I want to describe interaction between two particles, and this is 1, and this is 2. But in fact, since I sum over all of them, so these are the initial state. This is the final state. And since I sum over all of them, I simply put it as an upper. So I'll just write it like that. Draw it like that. Basically, this is time, this is space. What?
אתה מכפיל את מה שאתה מקבל בחצי או פשוט מכפיל?
לא, פשוט סוכם על הכל. I mean, this is just demonstrating over here. The upper particle emits a photon that later was absorbed by the lower particle, and here it's the opposite. The lower particle emitted the photons, A, B, C, D, A, B, C, D, gamma, gamma. Right here, particle A emitted the photon, turned into particle B, or quantum state B, which was then absorbed by particle C, which turned into D. And here it's the opposite. Now, since I only care about the initial state, this is the initial, this is final. A, B, C, D. Simply everything that is inside, anyway I sum over all of them, so I'll just write it like that. So these are, we said these are the virtual particle. And really we are summing overall. Summing over all possibilities. I told you these final diagrams are really some nesty integrals. Yeah?
How do we actually do the addition? Like, practically?
We'll see. We don't care. We don't care which one was doing first. Essentially, you're basically integrating over the entire time from minus infinity to infinity.
Integrate over what? Like the vectors of the...
We'll see. We'll see. One step at a time. Now just understand the concepts. Alright, I'll give you another example. Right. Now electrons can also become virtual particles. Okay. For example, if I want to describe pair annihilation, right? Annihilation. So E plus plus I minus goes into photon and photon, right? I can draw it like that. E plus gamma and gamma. If I want to describe scattering.
Wait, what?
What?
Time where's the time?
I can use electron as a virtual particle here.
Why?
Because it's allowed. If I want to describe scattering, so Compton scattering is when electron plus photon goes to electron plus photon with exchange of energy in between them. I can have an electron and a photon. Say that the electron was absorbed and it was re-emitted. I'm playing the same game. Yeah.
מה המשמעות של החצים בחימושים?
The arrows represent the charge, flow of charge. Time goes in this direction. Everything in between is virtual. I don't see. I just see the initial state. Time goes to minus infinity. So at time goes to minus infinity, there was an electron and there was a positron.
Okay.
And the time goes to plus infinity, there are two photons.
The flow of electrical charge?
Yes.
And in other examples, the So
Yes.
other charge.
No, just electrical charge. Here again, I started, at t equal minus infinity. I started with an electron and a photon. I ended up at t plus infinity, again at electron and a photon. Everything in between, there can be many things, but these are virtual. I cannot see them. But I describe them like that. Then I'll have to add them, given each one the correct coupling constant, that I can actually calculate what is the probability for something to happen. It works perfectly. What's called a Baba scattering. Baba scattering is electron-positron scattering to electron-positron. So it's called a Baba scattering. With an electron and a positron, they can change a photon and then get out as an electron and a positron. There is also this possibility: electron. Hey guys, questions to me?
Whatever with you.
No. Here they annihilate.
Okay.
Exchange the photon. Here it stays the same. It just changed the momentum. It's a virtual photon. Yeah, it's a virtual photon. Of course, when I want to calculate the probability of this process to occur, I need to sum over all of these possibilities. Yes?
When can I think of the arrow like, of the straight arrow like Zerem?
Yeah, current, yeah, flow of cards.
But whether the electron goes down or the positron goes up, the current will be the same.
Time flows always in this direction.
Mm-hmm.
Always. Up and down here is just for presentation. Don't take it too seriously. Yes.
The G that you showed previously that was 1 over 137, is there a theoretical way to predict it, or is it just experimental?
No, it's an experiment in atomic physics. And it actually it's not constant.
It's not a
It's not
constant?
constant. It's called running. Well, I'll mention a few words about it. It's called a running coupling constant. It changes with energy. It's not a real constant. Yes.
The way you drew the arrow on the positron, is it like going back in time?
Yes. Yes.
What is that?
Works. You can have the same description as a positron electron going back in time. And it works perfectly. We'll describe that when we discuss Dirac's equation.
Okay.
It is, yeah. Mathematically, it works fine. That's why Dirac got the Nobel Prize. Yeah.
If we measure it before and after the interaction, how could we know what happened in between?
Well, that's the whole thing. We don't know, right? This is again. This is an important question. This is a theoretical way of describing what we see, right? We don't measure that. Everything here is virtual. We need to sum up over all the possibilities. What we measure when we make an experiment, we know what were the initial conditions. We know what are the final conditions. Initial conditions mean time goes to minus infinity. We know what are the final conditions. That means the time goes to plus infinity. But there is some interaction. We know that the final conditions are not the same. This is how we calculate them. And miraculously, it works. Okay, but really, right? You have to integrate. You're asking what does it mean integrating that? Yeah, so it's integrating over all options over all times from minus infinity to plus infinity. But instead of writing these huge integrals and annoying integrals, it's much simpler to draw these diagrams and to tell you, right, for this vertex I add up some g, and I know what is the value of g, and I show you how to make an integral over these g's, and that's it. And we're done with that in 5 minutes.
That's it.
But that you know how it came, you have to have a course in quantum field theory. Yes.
Who are the people who invented this method?
What?
Like what we said, yes. Like to integrate over all the
It's why it's working. I mean, it's closely, philosophically speaking, there is a close connection to finite path integral. To the idea that particles can go through all the passes in space, basically. Optics, Snell's law, whatever, right? That particles can go through all possible passes that it can go in space with some probability. The logic is the same. Yes.
But here you say every possibility is the same probability.
No, I didn't say that. I said that there is a coupling constant for exchange of a photon. Now you can exchange 2 photons. You can exchange 3 photons. You can exchange million photons. You need to sum over all of them if you want to do the calculation properly. But practically you don't, because G is so small, so 2 is basically enough. This will be a correction. If you do 4, it will be a correction. If you do 6, it will be like... Yes, guys. It's fascinating to some of it.
אתה חיברת את שני הדברים האלה, יכול לעשות אותם לעזור?
The time here doesn't matter. What I care about is the initial condition that t goes to minus infinity and the final condition where t goes to plus infinity. Minus infinity. 0 is word interaction, of course, right? Minus infinity, far, back in time, they didn't know about each other. And far into the future, they will not care. In between, they're interacting. Okay, so we will essentially need to do integral from minus infinity to plus infinity over the probabilities of their interaction, etc. Yeah? That's it. Have a good weekend.